dynamic analysis comes if the engine requires carburetor.
The engine requires carburetor. Okay.
In carburetor, we use that energy equation as well as Bernoulli equation to understand how the fuel is getting into, means mixing with the air. For that,
Okay.
but that few basic fundamentals of aerodynamics, as well as the when air fuel mixture comes into the engine, the pathway, means from the intake manifold how it comes. There are few analysis there.
Okay. That is good, but I will just, it's not a question, but just if you have time, then later on you can let me know what is your idea on this, or else if you don't have any idea, you can later on try figure it out. The question is, what do you know about the compressible and incompressible fluid, incompressible flow?
Incompressible flow.
Hmm.
Sir, if means mathematically, if we can say that if the if uh, divergence divergence if divergence of velocity vector is equal to 0, then it is incompressible flow. That means that the flow is not compressing with respect to time. It's not compressible with respect to time. Uh,
Divergence. Okay.
Velocity vector is equal to 0.
So what happening to the density?
The density also changes with respect to time. If it is if it is incompressible flow, the density does not changes with respect to time. But if it is a compressible flow, then the density changes with respect to time, from also with space.
Okay. And is it anything related to the velocity of the flow? Compressibility is related to any point of time. Is it related to the velocity of the flow?
Velocity of the flow means that in that mathematical equation, that divergence or curl of velocity vector is equal to 0. From that we can say that it is incompressible.
Okay, that is also correct. But can a subsonic flow consider a subsonic flow and supersonic flow?
Yes, sir.
Not supersonic. Subsonic, incompressible, subsonic, compressible. What do you understand between subsonic compressible, subsonic incompressible?
Subsonic compressible flow and subsonic incompressible flow. So first of all, if it is subsonic, that means it is the Mach number is less than 1. And if it is compressible, that means the density of the flow is changing with respect to time. Uh, and if it is not changing with respect to time, then the density, means del rho by del t, will be 0 for incompressible flow. So apart from this, means
No,
with
nothing
speed.
to worry. We are just discussing the things. We are not questioning you anything. I mean, I'm not questioning you anything. I'm just discussing with you. Del rho by del t equals to 0. What does it mean?
Incompressible flow means it is not changing with time. The density is not changing with time. As well as divergence of velocity vector is equal to 0, then it is incompressible.
So velocity vector equals to 0. Then also it is incompressible.
Yes,
So
sir.
don't take it as any questioning section. We are just discussing this. By discussing, we are learning it. Okay.
Yes, sir.
So
Yes, sir.
my question is, suppose we have a condition like that m is approximately equals to 0.3. You have an flow field of compressible, and this is compressible. We have m equals to 1. It's a sonic region. You can you recall this? Supersonic.
Yes, sir.
Equal to 5. This is hypersonic. So what happening in this region? This is a subsonic region. We call it less than equals to 1. This is subsonic. So this incompressible region, as you're saying, that L dot V bar equals to 0, and dou rho by dou T is equals to 0.
Yes, sir.
So these things are happening.
Yes, sir.
So is it anything related to the speed of the flow? Because I'm mentioning that Mach number as a condition here.
Yes,
Is it
yes,
anything
sir.
related to?
Yes, sir. There is a relation between the Mach number and compressibility, uh, but I can't recall that, sir, equation.
Compressibility, we say as the definition, formal definition is change in the like K of what is actual definition we are stating for this change in volume per unit volume on application of unit pressure, right?
Yes, sir. Minus del V by V, I think, sir.
I'm talking. Okay. Just- So that is the standard definition actually for the compressibility, but here we are looking for incompressible flow with respect to the velocity of the fluid. As your flow velocity is increasing, what is happening to density? Do you know about this? If your flow velocity is increasing, what is happening to density?
Sir, if we consider the flow is to be incompressible, then can we apply Bernoulli's theory in Bernoulli's equation in it? Means if the velocity is increasing, then from that we can find the density.
No. From the velocity equation, you Bernoulli equation application was not only the incompressible things, some other things also there, right? So you are
Yes, sir.
satisfying all those things, you can find out the density from there. But in that Bernoulli equation, you have left and right the same value of density.
Yes, sir.
Density should be same. But my question is, so people have a confusion like from the aerodynamics side, they have the always phenomenon in mind like incompressible flow is the one that has a regime of Mach number less than 0.3. Mach number less than or equal to something 0.3. The flow is incompressible. So when I state this kind of definition for any incompressible thing, you may ask from your understanding of IC engines, when I have a piston kind of arrangement here, and when I compressing things or whatever the fuel air mixture that is coming, when I'm compressing the things here, where is the velocity here? Am I creating any velocity to the fluid? But here we are compressing the things and the density gets changed.
Yes, sir. Means
Like there is no velocity here, right?
no, sir.
There is no velocity, but there is a compressibility.
Yes, sir. Sir, that we
So
call, I think, the ram effect in high-speed engines.
hmm, yes, that is so compressibility is not only with respect to flow, but we have to state the things clearly, whether it is compressibility of fluid or compressible flow. Compressible flow is different with the compressible fluid. When you are compressing it, if it is a liquid, it is very difficult to compress. When it is a air kind of mixture, air and fuel mixture, because most of the part is covered with air, then your volume is decreasing and it is getting compressed, then your density is changing. It is a compressible fluid. It is not a compressible system. It is a compressible fluid. It is not a compressible uh, flow. Okay. So you should be careful like what they are asking, whether it is the compressible flow they are saying, a compressible fluid they are saying. Compressible flow in the sense you have to relate with the velocity, and compressible fluid in the sense you have to check what kind of fluid they are feeling. Okay. So that's just one caution kind of thing I just want to mention you. So let's take up the discussion to the further level. So how far like you have completed all the lecture sessions, assignments, everything?
Yes, sir.
So any queries related to the last few topics?
Sir, actually, I have a doubt regarding the 11th assignment.
Assignment
There is a
11. Okay. Hmm.
there is a mistake in that sir assignment that two questions are similar,
Hmm.
but I have ticked the answers also similar answers I have ticked, but
Hmm.
one answer came right and one answer was wrong. So due to that, sir.
I remember seeing that the NPTEL team, like whoever handling that particular kind of thing, they sent information that that second question or first question, they are not, I mean, one question they are not going
Second
to
question.
evaluate. Yeah. Did you get that mail?
Yes, sir. No, sir, I haven't got that mail.
I remember seeing it. Assignment 11, problem 11 of assignment. This one. Yeah. Assignment 11, question number 5 and 6 are exactly different. Yeah. Then they are not going to consider those things.
Okay, sir.
Yeah. They are not going to evaluate those things. So evaluation is based upon their correct answer or correct question. Okay.
Okay,
So they
sir.
will remove that. Yeah. Any other? How about your practice of learning other things in aerodynamics? Like you, you got any interest in the experimental side? So far, you learned mostly the theory part, and these days, like last few lectures are completely experimental things. So how is your understanding?
Yes, sir. Yeah, in the last 2 to 3 weeks, it was quite interesting. Means the experimental part was quite interesting. Means how particle image velocimetry was for
Okay,
quantitative analysis of the flow as past an airfoil or any other surface. For
okay,
so it was very interesting. Sir.
okay. So is there any other one in the meeting? Like to have any questions? Like Arvind or some other? Okay, if no questions. So, Arhit, if you have any questions, let's finish up. I mean, doubts or questions for you regarding these things. We can finish up those things and we can proceed for our session today.
Uh, Sir, let me recall, sir, once. Means-
Yeah, you take your time, and or else shall I start the session?
Yes, sir.
We
You can
can
start.
discuss at the end of the today's.
Yes, sir.
If that is the case, let me start this session. So, welcome everyone to this session of Fundamentals of Theoretical and Experimental Aerodynamics. This is a week 12. The course instructor, Professor Arnav Roy from the Department of Aerospace Engineering, and myself, Gangadhar Venkatramana. Today, we are going to see a few problems related to your course content, then any doubts regarding your understanding. So, without any delay, let's go to our problem solving sessions. Just a small recap of what we have done last time. These questions are related to your experimental flow isolation kind of things. So this question is asking that it's just number of flow isolations are there and asking what are the names of these kind of flow isolation. We can say it's oil flow is there, smoke flow is there, tuft flow and dye flow isolation. And similarly, we have some other question that's a kind of critical analysis that you have to think about this while answering this question that we discussed elaborately last time. The question is stating that you have a convergent divergent nozzle, and with this convergent divergent nozzle, how we are actually like measuring the pressure with the pitot tube, and if you have an idea of theory, then this theory can give the pressure distribution inside this convergent divergent nozzle. So the question is also asking the same based upon your theory analysis, or you are just doing an experiment with from your theoretical understanding that the pitot tube you are placing here. It's not a pitot tube, it's like a static tube that you're placing here and you're moving inside along the central line of this convergent divergent nozzle. And it is asking that how this pressure is varying. So we clearly discussed this, how this pressure is varying inside a convergent divergent section. And then another question we have is about a manometric fluid. Say it's a kind of the basic fluid statics, I can say. Like you have a pressure differences between two ports, like on the wall, if you consider this is the test section, and you have two different ports, port one and port two, and these two ports are connected to a YouTube manometer. And we have a question like there is a pressure difference or head difference inside this manometer, which is filled with the mercury, and this difference is around 2 centimeter, and they're asking just how much of actual pressure difference in kilopascals in the test section. So that is the one question. It's a simple fluid statistics, I can say. Fluid statics, I can say. Uh, and let's go to the next question, which is related to our Rayleigh tube concepts. Let me take time for it. So we have a question like stating about a Rayleigh tube, which is specifically for, like I can say, this formulation that we're going to use for this pitot tube that are related to the supersonic flows. So that we are using in a supersonic wind tunnel. This pitot tube, consider this is just a pitot tube, and pitot tube we are using in a supersonic flow where our Mach number in the tunnel is around 3. Is Mach m equals to 3. If the wind tunnel wall static pressure is so zero point 0.2 atmosphere, calculate the stagnation pressure measured by the Rayleigh pitot tube in atmospheres. Because question asked is into we have to convert into the atmospheres and assuming there's some constant given. So if we see this, um, this is like say a supersonic flow is happening here. Let's draw the schematic image of what we are doing here. So when we are looking at this supersonic flow, it's coming here, and then you have a pitot static flow that is trying to measure this inside this test section, which is coming with a Mach number m equals to 3. You will see, since because it is a supersonic flow, you can experience a very small bow shock kind of phenomena inside this. I mean, head of this pitot static probe. So this bow shock, what actually it does is it whatever the P naught here will pass through this normal shock. Like I say, it's though it's a bow shock, where for a very small amount of distance we can approximate this is a normal shock. So this P naught, whatever in the upstream of this bow shock, we can say that P naught P01 will reduce to P02. So because of this shock effect, we lost some amount of stagnation pressure. So the pitot tube also measures this stagnation pressure, that is P02 instead of P01. But our free stream is coming with the stagnation pressure of P01. So we have to careful about this particular uh, point while we are trying to uh, measuring the supersonic flow characteristics. So we have an additional information that the wall static pressure is zero point 0.2 atmosphere. So we are now measuring the wall. Also, we have an information the wall static pressure. So we are not. It's not a stagnation pressure. It's a zero point 0.2 atmosphere. If that is the case, the question is like what is the actual stagnation pressure, or not actual stagnation, what is the actual stagnation pressure of the free stream? That is the question we have. So from the Pitot Rayleigh-Pitot formulation, let me write this equation so that we can better understand how we are creating this Rayleigh formula with the idea that we just discussed here. That is P1 by P02 is equals to 2 gamma by gamma plus 1 m1 square minus gamma 1 by gamma minus 1 by gamma plus 1 power 1 by gamma minus 1 is whole upon gamma plus 1 by 2 m1 square whole power gamma by gamma minus 1. So this is your Rayleigh formula for this kind of phenomena when the Pitot tube that you are measuring and formation of bow shock and loss of stagnation. So if this is the case, what we need is P0. Like I need to clearly mention that what is this P02, the measure using so it's so now we have the all the details of this readings, that how we are calculating this stagnation pressure using the Rayleigh-Pitot formula. This is a kind of Rayleigh formula. We are now only focused on P02 with a direct static pressure information. This is the completely directly like if I say I can modify it according to one more condition. Let me just reframe this. P1 times gamma plus 1 by 2 m1 square times gamma by gamma minus 1 by P02 is equals to 2 by gamma plus 1 m1 square minus gamma minus 1 by gamma plus 1 whole to the power 1 by gamma minus 1. So this is the P01. This is the P01. If you see carefully from this equation, this is the P01. What is the stagnation pressure? Actual stagnation pressure, I can say. Stagnation pressure in the free stream. So this equation is the relation between P01 and P02. That is the loss of stagnation pressure, the ratio of stagnation pressure ahead and down behind of the normal shock wave. So that is what P01 and P02 we can relate to that. If you can relate to this P01, P02, you can see what is the details of. Give me a second. What are these details of P01 and P02? And this is a normal shock uh, relation to calculate the stagnation pressure ratio. So the question is now asking about calculate only the stagnation pressure measured by the Rayleigh-Pitot tube. It is not asking us to calculate the P01. So if you want to calculate the P01, you have the wall static pressure, that is itself is the stagnation static pressure of the free stream flow, that is P1 you have here, and you have the Mach number here. So these two are sufficient to calculate the P01. But the question they asked is to calculate P02, that is what actually measuring by the Pitot tube. So that's why they clearly mentioned it's not like, I mean, they mentioned in terms of the experimental point of view, not in the point of a theory. The theory can easily say that P02, calculate P02 means measure the stagnation pressure behind the shock wave. But it is asked in such a way that in experimental point of view, calculate the pressure measure or the stagnation pressure measured by the Pitot tube. That itself is same as P02. So That is the meaning uh, hidden in this entire question. It's application of your theory that you learned in previous chapters or previous content that you have to apply here. And this experimentals of experiments of fluids on fluids, or it's a supersonic or subsonic, whatever it is. So that if you apply the same thing, then you need to now have the target of first finding this P01. So how you can find out this P, because we need to finally get the value of P02, that is the stagnation pressure behind the normal shock wave. Though it is like we can simply solve it, we just try to rephrase the things so the picture can be clear, like what are the things involved in this entire equation. This particular part, I can say, like as I told, this is this term, the numerator term. Whatever this numerator term is, uh, the ratio of stagnation pressures across the normal shock wave, where the denominator term they just shifted for our convenience based upon the question, because the question information in such a way that it only has information of static pressure and the wall on the, which is the common thing that we can get on the wall of the test section, but it does not have the information of P01. So how with that information, and we have already information of the Mach number. So with that information, let's calculate the P01, because uh, it is the 0.2 atmosphere. As the Mach number is non-dimensional and gamma is non-dimensional, as everything is a non-dimensional, I can use directly this P1 as a zero point 0.2 atmosphere. And if I do that, and if I substitute this gamma equals to 1.4 and m1 equals to 3 m square, this will be 1.4 by 0.4. So this will be your P01. If you can calculate that, you will get approximately 10.08 P01 power 3.5. This is the value you will get for the P01. And also now we need to calculate about this particular parameters, particular information numerically. So just substitute the values that you have, because this all information that you know, it's not a new information, that is 0.4 over 2.4. If I do that, it is 1 by again 0.4. This value you will get as around 10.33 times 2.5 power 2.5. So this is this is what we use P01 by P02. Now the target is to find out P02 as P01 equals to 10.8 power 3.5. So then simplify this for the, if you try to find for the P02, you will get P02 equals to, I can say, 2.414 atmosphere. 2.1414 atmosphere, this is the one. So just as you have the ratio of P01 and P02, you also have the value of P01. Now you need to find out the P02. Then it will come your P02 as 2.414 atmosphere. Okay, just a minute. So this is the way that we can find out the value of uh, stagnation pressure that is measured by the uh, pitot tube. So basically, if I have to say, like in experimental purview, like one has to take the readings of what is the static pressure or the stagnation pressure in the supersonic flow. They actually first get the data of uh, P02 only. So the information, if you are doing like any test section, say consider this is the test section that you are trying to investigate the properties of a fluid that is coming or passing through this test section. It is more or less uniform, that we always try to generate a uniform flow in this test section to test various kinds of objects, whether it's cylinder, wedge, or aircraft, anything. So the primary thing that you or any experimentalist do is they actually put a pitot tube somewhere in the flow and try to measure the value of whatever the value reading that getting by the pitot tube. If you're using the meter, whatever, it will show only, it will take the reading of P02 only, because the pitot tube can measure only P02. And we don't know the information of Mach member. No one, it's not possible to directly know the information of Mach member. It is actually the reverse process. What we need to do is first let the flow coming at some kind of velocity. Assume that you set all the pressure differences in the wind tunnel, stagnation chamber, and this static chamber is sufficient to generate some particular value, but we are now still checking using the pitot tube. So this pitot tube is measuring the value of P02 only, and you have a static pressure port here, and that is measuring the value of P, I say P1, it's a static pressure value. So this P02 can only give this particular value. Now you have to find out what is this P01 from this ratio, because we already have this ratio, that is, no, we have only P02, and we don't have the information of P01, and using, it's a backward, we have to go, like not in the forward direction what we gave, we have to go in the direction of the backward. So with that information of the P02, you have to next calculate this backward information of all the like Mach member from the static pressure data available, or the and then P01 details. So the pitot tube can only give the details of your P02 only, but not your P01. So the question that directly we get already the information of static pressure and the Mach member. Okay, so these are very good information that contains in this question, like how a test section can be calibrated, or the properties of the velocity can be measured in the test section, or very good is present in this question. Like one can get more details of understanding if we properly understand the entire importance of this question. So let's go to the next question. So in this question, we have a details like I remember it is not correct. Yeah, we discussed this already, this kind of question I hit with. I remember discussing this question with you. Let me read this question again. You have a boundary layer. Yeah, we have the boundary layer. Thickness is obtained by traversing the boundary layer probe from the station close to the wall. Like, just let me try to schematically represent the things. If you have a boundary layer like this, and uh, close to the moving towards the edge of the boundary layer. So you have a probe, some kind of probe that is measuring some property inside the boundary layer, and you are moving uh, from close to the wall to the edge of the boundary layer, like in this direction you are moving, and you are measuring something here, whether it can be velocity or any other property that you are measuring here. So towards the edge of the boundary layer, the experiment conducted for 3 cases. So as you are moving, like suppose you are measuring the velocity only. So whenever you are measuring these, conducting these kind of experiment, 3 different cases are investigated. And those cases are first case you were neutral, favorable, and adverse. These are all pressure gradient. At these 3 cases, neutral, favorable, and adverse pressure gradients, this investigation was performed. And this investigation done by the some pitot tube, and following all the conditions of theory, all the theory like how you want to measure uh, those kind of things, all these things are done and measured. Then another thing is these different cases are studied by using suitable liners on the wall of the wind tunnel. Like yeah, liners, it means liners, right? you have to particularly take the lines. These are nothing like you have to predefine uh, vertical lines where you are taking the measurements. And then the same streamwise locations are also used for measuring so that the growth of the boundary layer can be uh, compared for these three cases. So the streamwise locations, they are not changing, so that as a good comparison, they are maintaining the streamwise stations. So streamwise station means as along your x direction. So they are maintaining in the x direction. So in the particular location, if your boundary layer is not changing, but your location of measurements is not changing. So everything is maintained very carefully so that the comparison will be correct. Like that they maintain the thing. Okay. So in that condition, the highest and lowest boundary layer thickness would be recorded for the following two cases respectively. So as we discussed all these details, like if it is a flat plate, you cannot see this kind of adverse pressure gradient or neutral pressure gradient. I can say uh, a curved plate on some body. There you will see the effects of adverse pressure gradient clearly. So when you see the effects of this kind of adverse pressure gradient or neutral pressure, it's because of the curvature of the body. So you will see the highest uh, lowest boundary layer thickness when there is an highest adverse pressure gradient. Like what is this highest adverse pressure gradient where your flow gets separated already, that is represented with the adverse pressure gradient, where you will see the boundary layer according to the definition of it. You will see it is a separated region, then you have a highest pressure gradient according to the definition of the boundary layer. If I draw the boundary layer from here, this may grow in this way, as we discussed last time. Also we discussed, I can recall that. If this is your separation line, if I say there will be a recirculation zone here. Okay, in this recirculation zone, and say consider this is a curved surface or some aerofoil, and the boundary layer thickness always from the like from the wall to the location where you have 99% of your free stream velocity. So this is the adverse pressure gradient region. And in this region, you will see the largest boundary layer thickness, where in the favorable pressure gradient region, that is indicating that this particular, all this particular location before the separation, that is your favorable separation. So that is your favorable pressure gradient region. So this is the thing happening for this is not a simple thing to describe in terms of experimental, because you have to compare uh, in in a perfect way I can say, in a meaningful way, such that uh, the neutral pressure gradient or the favorable pressure gradient, the definition should not uh, void, or at the same time your measurements what you're taking also very carefully you need to measure. And while applying the boundary layer, like Bernoulli's equations at the boundary layer, also you need to justify many things, like why we are taking the reading, is it possible or it is correct to take the readings at this particular location. And the comparison also you have to take in such a way that no other things are affecting as you move or as you change your pitot tube. So it's not a simple thing as we are reading in the uh, theory, or as we are studying in the theory. To make these measurements, one should be very cautious and very active in understanding or in relating the conditions, whether it is measurements or same that or same kind of scenario that we performed for uh, favorable pressure gradient while calculating the length of the favorable pressure gradient, or while calculating the length of adverse pressure. I'm saying boundary layer thickness. I'm saying length means boundary layer thickness. So these conditions should be same. Like if you are doing one set of experiments for measuring this particular kind of favorable pressure gradients in one particular time, and you are stopping the wind tunnel or experimental setup, and later on you are trying to measure for experimental data for this adverse pressure gradient, you will get, may not get, or may get these kind of phenomena. It depends on, because several things. So at a one go, or at a one similar kind of situations, environment, you have to perform all these experimental studies. So compared to the studying this theoretically, it's practically visualizing or practical measurements, or it's really time taking, but it is very meaningful if you have the practical data of these kind of uh, understanding of the physics, of the entire physics on adverse pressure gradient or favorable pressure gradient and these kind of questions. Okay. Yeah. So
Sir, I have a question.
yes, sir.
Sir, in this question,
Mm,
in place of using sir a petrostatic tube,
mm.
if we use the PIV technique, sir, will it be will we be able to see the flow separation in that case?
Yes, you can see the full separation. That depends on how perfectly or how accurately and carefully you are doing the PIV measurements.
Okay.
Yes, you can still see the separation, and the recirculation region, vertices, everything you can uh, very neatly you can visualize with the PIV.
Okay, sir.
Yeah. So let's go to the next question. I think it's recording, right? Yeah, it's recording. So in our next question, now we are looking at a uniform incompressible velocity. See, the discussion that we started at the beginning is very clear here. The question itself very clearly stating that nothing like compressible fluid, nothing like incompressible fluid. They're clearly mentioning that a uniform incompressible velocity u1. Why they need to mention that is a velocity? Because it's something that is related to the flow. It's not something that is related to the fluid. The flow velocity is making the things changing to compressible or incompressible. So that is why we need to mention there is a flow or a fluid. So in uniform incompressible velocity u1, let me read the question. And free stream density rho approaches a symmetric aerofoil whose leading edge is located at 0, 0 and trailing edge at 1, 0. And its chord line is given by the equation y equals to 0. So just let me represent the things, the information what we have so far. This is a symmetric aerofoil and its equation is y equals to 0. That is, it's located along the x-axis. This is 0, 0. This is 1, 0. Yeah. This is your leading edge and trailing edge. After crossing the airfoil, the free stream velocity of u1. The question is after crossing the aerofoil, a velocity deficit occurs in the flow due to the viscous effects in the boundary layer. So let us see the, if I take a plane here, if I take a plane here, let me do this carefully. Yeah. So this plane, if you see the velocity at every point, it is almost uniform. I'm trying to draw these things almost uniform. So when this kind of velocity is crossing this aerofoil, there is something happening that what is this? The velocity deficit occurs in the flow due to the viscosity effects. So this velocity deficit will make this velocity profiles. Like if you take any line after crossing this aerofoil, like somewhere here, this profile, whatever the horizontal lines and the vector arrows I mentioned, this profile will get changed because of this velocity deficit, and that is happening because of the viscous effects in the boundary layer formed on the aerofoil, and in the wake of the aerofoil, this happens. So this velocity profile in the aerofoil wake is obtained at x equals to 3. So just assume it is not a perfect length, it's not a complete length, I can say it is, say, 2. That means it is already 1 here, and from 1 to this particular location where they measured this velocity again, that is 2 units ahead of this 1 comma 0 or the trailing edge, and which is 2 chord lengths downstream. It's the same thing they mentioned here, which is 2 chord lengths downstream of the trailing edge of the aerofoil, and is given by u2 of y. Say this is our first station, so it is like u1 of y. Why it is u1 of y? We are mentioning that velocity is a function of y. So as you move along the y direction, your u velocity gets changes. At the same time, this is u2 of y, where you did the measurements in the wake. So the wake velocity distribution is obtained from y equals to minus h to y equals to h. So what actually it is telling that? It is telling that that you, whatever the velocity measurements that you perform, you cannot perform from minus infinity to minus infinity in the y direction. So they performed only from some minus h to h, I can say like this. This is, let me erase this. This is minus h, and this is your plus h. So they did the measurements from minus h to h. That is like from this point to this point and this point to this point. I for the better understanding, it's a clear writing is writing minus h here is correct, and writing h here is correct. So and this is your 0, y equals to 0. So if you see this kind of profile, some kind of profile, I don't write the arrows, but velocity deficit, say, assume the velocity deficit because of this friction effect or the viscous effect. This is the profile. Okay. So if this is the profile, they're asking us to find out the drag per unit span on the aerofoil. They are not asking us uh, like about this profile. They did not give like any clear details of how the velocity profile is, but they're just asking. They're given the function of u1 of y. So it can be some other function where u1 of y is a uniform, where u2 of y is some momentum deficient. That means there is some loss of velocity in this momentum just behind the aerofoil, and it can be represented like this because some momentum deficient they are seeing. So velocity deficient or the mass deficient should also be there here. So that can be represented in this way. That is from minus h to h. So now the only question is how you can find out this drag per unit span of the aerofoil. As you have so many options here, whether we can go for the option checking or we can see from the actual perspective of you. So to go into the much details of this question, I just let us take a few minutes break and then we can come back again. So let us join again on 7:05 p.m. It's okay?
Okay, okay, sir.
Okay, let's join back at 7:05. Okay, welcome back. Arhit, am I audible? Are you there? Hello, Arhit, am I audible?
Yes, sir.
Yeah, thank you, Arhit. So let's go back to the details of this question. So we've seen up to the velocity profiles and assuming this function now. Now the target is this, like how you are going to calculate the momentum deficit with respect to the uh, your understanding of momentum equation. So what we only need is to first take the momentum difference, the same minus h to h, and like at the point at the station 1, we have the minus h to h, we have to calculate the momentum, and at the same station 2, minus h to h, we have to calculate the momentum. So in that case, what we actually need to take uh, the mass, I can say the mass. We have to take whether the mass that consists here with respect to the state 1, this is the mass that we need to take, or the mass that it is crossing station 2, is this one we have to take. That's the first question we need to clarify it, because momentum, if I say the principle, and it's a mass in mass times the velocity, right? This is the momentum that we have the convention. Or if I clearly write in integral sense, integral of rho dv, it's a volume, integral of rho vd, integration of rho v dv, where your rho is a density and your v bar is a velocity, and your dv is the small volume. So in this way, if you are writing your momentum, so my mass in station 1 and station 2, I need to calculate the momentum deficient. I only use the mass that it is taken into consideration for these measurements of this momentum deficient velocity. That mass only I will take, and the same amount of mass I will apply the momentum at the station 1 and the momentum at the station 2. Like how, what is actually I'm telling? I'm telling that you have to take the mass should be as a constant at the same locations. That means if my momentum mass is m, say m, and momentum deficient is like this, that is u 1 at u sorry, I will write like this, u at y at junction 1 minus u at junction 2 or location 2. So this is the uh, momentum deficient, that's mass times uh, change in velocity. I'm just not completing the integration, I'm just writing the velocity functions at some point to point. So at y1 and y2. Or in the equations as they write, it's not like a y1 and y2, they wrote it as like u1 and u2. So in the same way, if I write mass times u1 y and u2 at y. So y, you should remember that y is a like this is two different positions of x. This is this and this. This is not a correct phenomenon. The y distances are same, but x locations are different. That is what u1 and u2. So now it's look like all the equations consist of the same u1, u2, u1, u2, u1, u2. So this is very clear. We have to integrate with dy across the along the y direction, but and from we know that minus h to h we have to integrate, and this mass can be represented with mass, or like if for a two-dimensional flow, I can represent dx, dy, dz. Okay, dx, dy, dz is your representation, and for a volume, any small volume, this is not I should not represent directly. Uh, say I will say dm. Now it's a dm into change in velocity at that particular location, and you are integrating from minus h to h. So mass times the small amount of mass and the velocity. So I can write this dm as dm equals to rho dx dy dz, where dx dy dz you are representing a small volume, that is dv, and your dz is a unit because we are considering in two-dimensional way, so it is a unit value, so it is now dx times dy. So dx and dy. And consider there is no velocity in the y direction, so my dm by dt will be rho dx by dt times dy. So there is, but consider there is no change of dy in the y direction, only u velocity is the thing playing, then it will be like dm by dt is equals to rho u dy, or m dot is equals to rho u dy. So if I replace the same with the dm dot, replace the same in terms of this dm, say it is here, instead of mass, like momentum per change of per change in unit time, that is dm dot. I'm just replacing this here. Momentum per change in unit time or momentum change, weight efficient, everything will comes the same way because we need the drag, right? So when we are looking for the drag, we need to differentiate with time. So that time differentiation we are doing with the change in mass flow rate, like that it is happening. We represent the dm dot. So I'm replacing the same thing, minus h to h rho, and what else? Yeah, u times u1 of y minus u2 of y, and the third one is what is the last thing? dy. So we almost approached the formulation of the thing that given an option A, B, C. So what is the final thing that we left is whether this is u1 or u2. That is the question. At the starting itself, I told, right, what is the mass that we need to consider for understanding the change in coefficient of momentum. We have to take the mass related to the amount of momentum that we are calculating, or amount of mass that is crossing this section, that is minus h to h. So the same mass that we need to multiply with the velocity at here and the multiply with the velocity at here. So then only you will get the correct momentum deficient with respect to the airfoil, and that is giving you a drag. So that mass can be obtained when you change this velocity as a u2. So now you see rho into u2 dy means this is corresponding to the mass in the this particular region, and also same that you're multiplying with the u1 y, that is momentum corresponding to this region. So this momentum minus same mass, rho u2 is the mass of at this particular location, mass period at this particular location, and then you're multiplying with the u2 at particular this location, that is the momentum deficient, that is a momentum present here. So as you're doing the difference, you will get the momentum deficient per unit time. That is nothing but your drag per unit span, because your unit span is indicating by Z. As we took already, Z is a unit one. So this is the correct formulation for this, and the same thing is shown in option one, and any option uh, U2, U2. This is U2 square. Yep, right. So A and D are the options that representing the same thing. They just took that U2 inside this uh, brackets, inside the braces, and it's the same thing. So the correct options are A and D. So Arhit, I hope it is clear for you. If it is not clear, let me know, because it is some kind of theory that is we are playing here. If you're okay, or any other one, if you're okay, then we can go for the next thing. Otherwise, we can discuss at this point.
Yes, sir.
Yeah. Yeah. Okay. If you're okay, then we can move to the next question. So the next question is asking us about the supersonic wind tunnel. It's about the supersonic wind tunnel. A supersonic wind tunnel is operated first with a wedge mounted in its test section, and then a cone mounted in its test section. Both of them have the same base area, which is used as a reference area of drag calculation. Drag coefficient is obtained by both the bodies found to be C dW. W is indicating the drag of the wedge, and CDC is the drag of the cone. This is wedge drag. This is cone drag. So that the two drag coefficients could be related. As one point that we need to specify, like it should be clear in this question that stating that the wedge is completely fitted in such a way that as a two-dimensional object, it is in such a way that they kept they kept this wedge. Wedge is nothing but this kind of wedge, and they kept it in such a way that this occupied the entire touch section span. So entire touch section span, this wedge length is occupied. So it is a kind of two-dimensional phenomena. Where comes to the cone, this is a three-dimensional phenomena. This is two-dimensional, and this is three-dimensional. So the point comparing between two-dimensional and three-dimensional, that you have a kind of concept that there is a three-dimensional drag relief. A relief of drag as the fluid is able to pass all over the body. It is not creating any blockage compared to the blockage. If I say in the very good correlation, I can say the amount of blockage. The amount of blockage creating by the cone is less compared to, though the base area is same. Base area means some reference area, whatever they're taking to calculate the drag between the wedge and the cone, that is same. But still, the blockage or the momentum deficient by the wedge is more because it is blocking the more amount of fluid, or it is not having any three-dimensional drag release. The wedge is more compared to the cone, though the reference base area is same. So your wedge drag is greater than your cone drag. So this is the suitable option for this. It's like I have to mention and one more point here. So whenever we are trying to do the experiments in the wind tunnel, as we are having wind tunnel or water tunnel, whatever it is. So assume, let me draw it. Assume the test section is lengthier, but not lengthier in the cross-sectional way. Suppose this is the test section for the wind tunnel or whatever the tunnel that you are, the supersonic or subsonic, whatever the test section is. So we test the bodies here. So when you fix the body aerofoil or something in this particular location, the flow always passes over this, but you are blocking the tunnel with some object. As you increase the angle of attack, or you change the shape, anything, you are blocking the flow to the tunnel, so that your blockage ratio should be within the less than 5%. Then only you can say whatever the readings that your blockage ratio means, whatever the fluid that you are allowing, if you're placing some obstacle here, that means it's placing some obstacle itself within the body, as the fluid cannot take the turn freely on the upstream, because it should be sufficiently spaced that it can accommodate the whatever the fluid turning here. If it is not that sufficient, your blockage will be more. The fluid will blockage and will accelerate on the top of the surface. Not only because of the fluid's airfoil surface, it also accelerates because of the converging effect here, because you are closing the, or you're decreasing the space for the fluid to pass. So these kind of conditions also we have to carefully analyze while doing the experiments so that our readings what we are taking are correct. Okay. Yeah. So let's me move on to the next question. So Arhit, can
Sir,
you answer this question? Yes, Arhit.
yeah, sir, in the last question, one
Okay.
thing I didn't understand because, sir, uh, in this you told the blockage by wedge is more compared to the pole, though the reference
Block.
space area is same. Why?
Yes.
Oh, you are
Difference.
attaching the uh, means with the two side of the wall. This wedge.
Yes. That is what the
Okay,
wedge is. Wedge is a
got it.
two-dimensional. We are spanning from left to the right. Okay.
Okay. Yes, sir. Got it.
So can you answer this question? I
Yes,
just
sir.
want to hear. Yeah. What is this?
First one is sting mounted. Second one is strut mounted, and third one is semi span model.
Yeah. Very good. So it is very clear. The naming from our the say, representation also it is very clear. First one is a sting mounted, where you mount the model in the way that we are seeing in this particular image.
Uh, Sir, 1 minute. Can you able to hear?
Yes, Arvind. Yes.
Actually, in some of the assignments,
Yes.
some options were wrong or options were not available. Actually, I conveyed by message. I sent email, uh,
Okay.
but we have not got the marks corresponding to that one.
Your
Can
email,
for
can you tell me your email?
nagurkar123@yahoomail.com.
Yahoo Mail.
Regarding assignment number 11, question number 6, actually,
You posted the discussion in the groups?
uh, hello?
Yes, yes, I can hear you, Arvind, but have you posted your query in the discussion groups?
I sent by a message, actually, Yahoo Mail, to
To
professor
whom?
also.
Okay.
Uh,
So stay, can you, if you are using a laptop, can you show me the things, which question that you are looking for? If something
one
is
minute,
not
I
yet,
will show you.
yeah.
Uh,
Can you share
this,
from your end? Can you
uh,
share your screen?
four strain gauges arranged in a different circuit in a fully Wheatstone bridge circuit. These strain gauges are mounted on a wind tunnel which is being calibrated in a calibration rig. Excitation voltage for the Wheatstone bridge is 120, no, sorry, 12 volt. The original resistances R1, R2, R3, R4, 120 ohm. On the application of lift for 50 Newton, the values of resistances R1 and R4, 118.8, R2, R3, 119.2 ohm. What is the applied force if the bridge output voltage is 0.01 volt? Actually, it will come as a 25 Newton. But
Okay.
you have said it's a 50 Newton. That is the assignment number 11, question 6.
Assignment 11, question 6.
Uh,
Let me see whether some other students also posted it or not. Because recently I saw some students posted it and we also responded for that, the corresponding TA. Let me see. Assignment 11, question number 5 and 6. Is it?
uh, 5, okay, 5 it's, but these both are same questions.
Hmm. Yeah. If you can see, uh, like I will show you this mail. You can get clarity with that. Let me share my screen. Because I don't know whether you are there in the Google group discussions or not. But yeah, can you see this mail? So one of the student, Talapati Kaumudi. So she is asking the same question, like both questions are same. No, no, not this question. I said 11. Yeah, this one. Yeah, this one. So assignment 11, question number 5 and 6 are exactly same, to different answers accepted. So they are stating that the professor or the corresponding person, and they are stating that it's a kind of error from our side. So we are not going to consider it for the evaluation.
No, you are not considering for the
That
evaluation.
question for the evaluation, yes, they will
And
update
one
it.
more is there.
Yeah.
One more I will tell you. Assignment number. Assignment number 7, question number 4.
Assignment number 7 and question number 4. Okay.
See, in this, you are asked, see, which of the following statement about the formation of velocity boundary layer in the flow over aerofoil is incorrect?
Okay.
So, actually, correct answer you have put A and B, but
Okay.
D is also is correct, as there is a no favorable pressure gradient exists at location 2. Okay, but you have mentioned a favorable pressure gradient exists at location 2. But at location 2, which is at downstream of the aerofoil, there will be an unfavorable pressure gradient.
Okay. Let me just read the question, because I remember discussing this question in the earlier class, but
Sorry?
with your request, I remember discussing this question in the earlier class, but I will just look at it for based on which question? This is assignment 7.
Question number 4.
Assignment 7 and question number 4. Okay, yeah, this one we discussed it.
Actually, D option is favorable pressure gradients exist at location 2. That is not correct. So D is also is to be considered, because it has been asked which of the following statements about the formation of velocity boundary layer in the flow or aerofoil is incorrect.
Okay.
Yes, yes.
The favorable pressure gradient exists at location 2. If I'm not correct, I have a confusion with this all the time. Harihit, what we stated that favorable pressure gradient is dou V by dou X should be less. Dou P by dou X should be negative or less than 0.
Sir, for favorable? Yes, sir. It is greater than 0 for favorable. Dou P by dou X.
Dou P by dou X greater than 0.
Yes, sir.
No, less than 0.
Less than 0.
Sorry, sir. Less than 0. Yes, sir. For favorable,
Yes.
it is less than 0. And for
Yes.
unfavorable, it is equal to or greater than 0. So therefore, option D is also correct, sir.
Option B or option D?
D is also
option
correct.
D is also
A,
correct.
B, and D.
A, B, and D. Yes, sir.
Equal to or greater than 0. That is unfavorable. So what we pointed out last time, like, did I say that this I will take it to the corresponding person?
Yes, sir. But I think, sir, the score has been given after the re-evaluation. But in the assignment,
I sent, but I could not receive any positive feedback, because one more is there. One moment, one thing.
So just let me clarify one thing, Arvind, like whether they gave the score for this or not. Like question number 4 for option D, they gave a score for you or not? But Arihit.
Sir, in assignment, no, sir.
They did not give the score for option D?
No, sir. I have to check the progress tab once.
Okay, kindly check the progress tab, and if it is not given evaluation, Arhit or Arvind, can you please raise this question again in the discussion group, or please write a mail to me, or in the discussion group. It is also nice if you can send the things.
And for one more, sir,
Yes.
one more.
Yes.
Assignment
Yes.
number 6, question number 11.
Assignment number 6, question number 11. Let me point it out.
11.
Assignment number 6 and question number 11. Okay.
See, in
Yeah.
that one, determine the Mach number downstream of the normal shock if upstream Mach number is 1.75. Assume gamma is equal to 1.39.
Okay.
Okay. So you are saying that it is a 0.39. Actually, that formula is m2 square. Like this one formula is there, m square. So that m
Yes.
square comes 0.39. So if we take square root, it will be something between 0.6 to 0.7 or around that one.
Yeah.
Okay.
Actually, this question
So
is also has a mistake from our side. So we are also not considering this for evaluation.
yes, yes.
The team has
Okay.
pointed out all these mistakes. Someone also pointed
But
this earlier in the March itself. So this question is also not considered for evaluation.
I sent actually, but
Mm.
corresponding marks means adjustment of marks we are not got means.
They will
Okay.
do at a time, like maybe you will get updated at the end, because I also don't know when they will update and get back to you. But they will
Okay. Okay.
consider at a time all these mistakes, they review at once, and then will correct for all the people.
Okay. Okay. Okay.
Yeah,
Thank you, sir.
yeah.
Further.
Thank you, Arvind.
Uh,
Any further questions? Any more?
mm,
Hello?
uh, 1 minute. To increase the lift at low speed at a moment. And also,
Hmm.
there was a question.
Okay.
There was a question. Uh,
Hmm.
uh, what is the intention of using slotted flaps as a high lift device?
Slotted
Hello?
flaps.
Slotted flaps.
Slotted flaps is like you are maintaining the increasing the camber of the aerofoil.
Yes, yes. No,
Hmm.
there are three correct answers. Okay,
Okay.
it has been mentioned to avoid large scale flow separation under the adverse pressure gradient, to
Okay.
increase the lift at low speeds, effective tangential momentum injection into leeward flow. Okay, ACD. Okay, I agree, but B is also to slow down the aircraft because the lift coefficient is increased. The aircraft
Hmm.
ultimately it will be slowed down, na? During landing, etc. If you see.
During landing, we say it as a spoiler. Why lift coefficient
No,
increases?
flaps during landing also it will be used flaps.
No, no, no. During landing, we don't need the lift, right?
No, no,
That is
flaps will be used during landing. So,
okay.
lift will be increased. So it
Yeah.
will slow down the aircraft also. So
Will
B is
be
option
increased.
also correct.
So can I which assignment? Like I just want to read the details
1 minute. This
because
one,
I am
question number 7. 1 minute. I'll tell you. It is assignment number, na?
hmm,
Mhm. Priorities. I will tell you the assignment number.
sure.
अरे बाप रे.
Rohit, do you remember that question anywhere somewhere?
I will tell you just 1 minute. I am checking that one.
Yeah, I'm
Because
just like
sorry,
asking. Arhit is also there, so I'm just asking his opinion whether he is able to
sorry.
recall. Arhit is there.
Ye- Yes,
Yes,
sir.
Arhit. Can you
Actually,
recall that question from which assignment?
I can recall the question, but sir, from which assignment I have to just
Okay.
check, sir.
Yeah, yeah. Please take some time if you want to check for it. Which question. So is it a very early assignment or
Shall I
yeah?
send whatever my doubts are there in that one? Doubts in the sense,
Okay.
will you correct to your email address?
You can send. You can share to me my email address. I will write it for you. But I just want to see that question, like which question that we are
Yes,
discussing.
I will tell you. If you can share.
This is my email address. You can get to.
What done? 1 minute. Your email address is
Can you see this? I'm sharing
just
it this time.
1 minute. I will note down.
Yeah.
Uh, Tell me, I am writing down.
Yeah, I just shared on my screen. Like if you want to.
Screen you are
Yeah.
sharing. Okay, 1
Yeah,
minute.
I shared.
PG PGV PGV Ramana.
Yeah.
PGV Ramana @KG. Okay.
Yeah.
That just 1 minute. I will tell you.
Are you sharing the question with me through email?
Just 1 minute. I will tell you.
Okay.
1 minute. Sir, my question 11. Question 11. Question 2. Question number. Excel. Uh, Assignment number 7. Question number 7. It's
Assignment number 7.
question number 7.
Question number 7. Okay. So we are in the same assignment. Yeah. What is the intention of using the slotted flaps as a high lift devices? Okay. So
To avoid large scale flow separation, okay.
Mhm.
Under strong adverse pressure gradient,
Mhm.
then increase lift at low speeds, okay. Effective
Mhm.
tangential moment injection into levered flow. That is
Mhm.
also okay. But it slows down the aircraft also, na? We
No,
required
no,
less lift during landing.
no, it is not for the during the landing.
We
Yes,
we sorry,
yeah.
lift is increased. We required less speed during landing.
Yeah, I will tell you this background behind. Let me take a.
And also, if we this one, what I am saying, if we deploy the flaps, as the lift is increased, drag also
Hmm.
increases. So definitely, it may decrease the speed also. Hello.
Lift increases, drag increases, but here you're missing one point actually. It is not only the couple of lift, drag, and velocity, but it is also the couple of thrust. There is one more parameter that thrust is also involving in this.
Oh.
So the drag is always getting balanced by the thrust force that is generating. So as when the wing,
Hello.
when we yes, can you hear me?
Speak loudly, little.
Okay. So the moment that you are using the flaps to deploy,
Uh,
it may not
uh,
be the correct representation. When you deploy the flaps, it is actually to increase your lift by increasing the camber.
Increasing the lift. Okay.
Yes,
If
yeah.
we increase the lift,
Hmm.
speed is also required less.
Speed is not required less. I'm telling only about the takeoff. We will come to the landing part. We
Takeoff
will
you are
come to the.
considering.
I'm
Okay.
considering the takeoff. We will come to the landing
Uh,
part. So when you are when you are deploying this flap, and
uh,
then lift increases and drag is also increases, but this drag during the takeoff compensated by the thrust. So
by the
thrust
thrust.
or
Uh,
thrust, they increase the thrust.
yes.
So they don't compromise with the lift. So they increase the thrust by to overcome this drag, whatever the drag presented here. So
Uh,
let's come to the landing. Landing, your question is to decrease the velocity of the aircraft. Yes,
uh, uh,
to decrease the velocity of the aircraft, I can deploy this particular kind of device. I can say, let me say, I will just name it as a device, but not a flap or spoiler. If it
sorry.
is like to decrease the velocity, I'm saying about to decrease the velocity, why do I need to deploy this flap in downward direction? I can deploy the same thing in the upward direction also, right? This can also decrease my velocity, isn't it? And I also have an additional benefit by deploying my device in the upward direction by decreasing the lift. I can decrease my lift because I need to land. So to land, we need to decrease the lift on the aircraft, and also we need to reduce it. So we are increasing the drag by deploying this spoiler upward, and we are also decreasing the lift, and we are also decreasing the velocity by increasing the drag. There we don't increase the thrust.
But whatever might be, lift as lift we are increasing. So little velocity, it slows down the aircraft also. I think so
For
because
landing,
lift during landing.
yeah, one problem with this deploying in downward direction, it increases the lift. Whatever the lift velocity it has, that is the another thing. But also it increases the lift because you are increasing the camber. Assume it is now at the velocity of say 30 meters per second, because unjust is not a normal thing. It's just a value, approximate value, 30 meters per second. The like any vehicle or an airfoil is. Now you deployed this flap in the downward direction. And let's assume the lift comes to, the velocity comes to 25 meters per second, as you said, to decrease the velocity. But what is the increase in lift? The corresponding increase in lift will be higher, right? Which is not at all required during the landing. The priority in the landing is to decrease the speed and to decrease the lift, isn't
Decrease
it?
the speed. Decrease the
Decrease
speed.
the
But decrease
decrease
the
the
speed
speed
means to slow down the aircraft only.
to slow down the aircraft, but that is not we are doing, right? Because we don't want the lift also at the time. We need to spoil the lift at that is why we say it as a spoiler. The question is in the practical sense, if we are not using this flapping for decreasing the lift during the landing, we don't consider it as an option, right? because we are
Okay, not
not using it for that.
considering, but okay, it may slow down the aircraft a little.
It may slow
I'm
down.
not
Yeah,
saying,
it may slow down the aircraft. Yes, that's true.
but
Only in terms of the
we are
velocity.
not.
I am also stating the same.
It will slow
Uh,
down the aircraft, but
yes,
that's what. So that's what I felt. It will slow down the aircraft after
mm,
deploying the flaps.
yes.
Uh, but
It is. It slows down the aircraft, but that is not the intention, right? For using high
not
lift
intention.
devices.
Okay, that is not the intention, but it will
Yes,
slow down the aircraft.
yes, it will
Okay.
slow down the aircraft. That's
Yes.
true. It
Okay.
will slow down the aircraft. But the question is the use of high lift devices. Mostly, its purpose is for the high generation of high lift. Hope you are clear with this.
Yes. Yes.
Yeah. Okay. So, any more further questions?
To so what is the intention of using slotted flap as a high device? And also,
Any further questions, Mr. Arvind? Can I call you?
question 4 in assignment 3 option. Sorry, please check it. In assignment number 4, question 3, actually options are not available. Assignment number 4, question 3. A, B, C, D options are not available.
And let me check this.
Assignment number 4, question 3.
Question 3. Okay, option A, B, C, D. They left with the option A, B, C, D. What isn't it for?
Options are not available.
Options are not available. Maybe they will discard this question also. They will definitely discard this question. Let me see whether they discard this question.
They will discard this question. No? Okay.
And they will. Assignment 4. This is assignment 4.
Question 3. Yes.
Assignment 4. Question 3. Yeah. But they did not mention in this name. Assignment 4. Question. Arhit, are you there?
Yes.
Yes, sir.
Assignment number 4.
Yes,
Question
yes.
3.
Arvind and also Arhit, I request that if this question has no options, because I cannot raise this question because I am also a person in this. If Arhit and Arvind, if you can raise this question through email and also Google discussions, they will re-evaluate this.
Okay, sir.
If there are
Okay.
no options for it, they will re-evaluate.
Okay.
Yeah.
Okay. Some of the questions we discussed. Okay. I will forward the questions. Hello.
Okay. Yes. Yes.
Okay.
Yes.
Okay. Just check it up.
Yeah. Sure.
And sir, this one corresponding marks, whatever it comes, if you assign, it will be better, sir. Just see.
Corresponding
If you are
marks.
filling,
I just got a mail that those marks already updated with removing the mistaken questions or improper questions. They removed those things and they updated. If you can check in your
updated.
progress tab, yeah, they
Now
updated. I
today,
just got it. Yeah,
today
yeah,
updated.
just 20 minutes back, I got this mail.
Okay, okay.
You can
Then
check
I
in
will
your
check it.
progress tab. Yeah, yeah. Please check it
Okay.
and you can write a mail if it is.
Yes.
If any still more things are there, we can review this.
Yes. Yes, sir. Okay.
Yeah.
Thank you, sir. Thank you.
Thank you so much, Mr. Arvind, for pointing all these mistakes. Also,
Yes.
thank you, Harshit. So that is the case. We are already running out of the time, but we have just 10 minutes left, not running out of the time. So we can discuss one or two more quick questions. If you have any questions, or we can discuss the content.
Sir,
You can come. Yes, Harshit or Arvind? Yes,
sir,
Harshit.
Arif.
Yes, sir.
Sir, I have a question related that cross correlation analysis in PIB technique.
Cross correlation analysis. Okay.
Sir, in that case, in cross correlation analysis, if we are doing an analysis of an airfoil,
Hmm.
means the flow field over past an airfoil,
Hmm.
how we are making the probabilities that the particles are displacing, in the video
Okay.
professor told that we find the probabilities and we exclude those probabilities which are less probable to occur. So
Okay.
using probabilities only, we just plot the graph and reject the less probable ones.
Reject the less probable ones. It depends on the user code, user and code also. That is one classical technique. Probability in the sense, I will tell you, like, I don't know whether the same thing that you are asking or not, but with my understanding, if suppose this is your frame of view of your PIV and you have the interrogation, have you like these things you learned? That is there something
Yes,
like
sir.
interrogation?
Interrogation section. Yes, sir.
So this interrogation window, you are dividing some set of number of pixels, I can say, or interrogation windows. This consists of number of pixels. If you take any one particular box, I will just write that big box. If you represent at the time instant t equals to t1, suppose only these number of particles are there in my uh, not these many, just present few, very few. It's not based upon the probability. It's based upon 1, 2, 3, 4, 5. So based upon your time step and based upon your velocity, you got these kind of particles in your window in your small interrogation window, I can say. So at the next time instant, when you see 1, 2, 3, 4, 5. So this picture gives you very clear information that, sorry, this is the movement of particles, right? So
Yes,
it's
sir.
now one-to-one correlation. They will try to correlate based upon the pixel information or based upon the histogram information. They will try to correlate the movement between or the distance between of one each particle to particle. So the probability of all these same set of particles like this, or let me consider this all set of same particles, or had like the same thing that we captured in time t equals to t2. At time t equals to t1, we have this set of particles, and time t equals to t2, we have this set of particles and just move it a bit forward. So what is the probability of that only the same set of particles in this next time instant in the same interrogation window moved for some displacement? It is very clear that definitely this is the like I can say 99% of probability these are the same particles that move forward in time a very small amount of distance, isn't it?
Yes, sir.
But if you have very clumsy or number of particles very occupied or very less number of particles, like if you have more number of particles occupied at this time instant that completely occupied, and at time instant 2 also you have completely occupied, so what is the probability of the particles are the same from 1 to 2 window? How you can judge? Is it possible?
No, sir.
It is
We
very
cannot.
difficult.
Very difficult, sir.
Yes, it's very difficult to estimate. At the same time, if you have a very less number of particles, like only at this one instant, one and two particles, okay, and first particle moved up to this location, and second particle moved out of the frame, okay. There is no other second particle in the time too. It's moved out of the frame. Now there is what is the amount of probability that you can say this particle is the same particle moved this time this much of displacement, because you don't have any second particle also. So I can say it is just a 50%
Yes.
or less than that. So based upon this kind of estimation, what is the probability of the particles are the same that we are looking at time instant t1 and looking at time instant 2, we should able to use some objective function that is can give some fit high value or some kind of 0 to 1 normalized value, where you can understand that all these particles, like whatever the particles uh, that you are looking at a time instant t1 are same at time instant t2 but displace this much of distance. So you should able to create that function suitable to your application. You should able to create that function, because how you can create that function, again, that depends on your velocity. Suppose if your velocity is 0.02 and that velocity is sufficient enough, uh, like you can trace the particles between time instant t2, because you are moving it very slow and you're taking the pictures at good instant of time, so that this one. So at every small instance you are able to take the pictures, and this is your interrogation window. So your probability function always also involves this velocity function. That means because of my delta time step is very small, my particles cannot travel or cannot complete the distance of or cannot move out of this interrogation window. So that is also giving the probability that this particle should be or must be the same particle that I have seen in the previous time step, right?
Yes, sir.
Yeah, in that way, you have to define your objective function that can give the probability of the particles are same, and then we can correlate. Correlate means based upon the distribution of these particles, a one-to-one correlation, like a correlation of these particles to this particle to second particle, one-to-one correlation, and which correlation is giving you a good value that is the correct distribution of the particles.
Yes, sir. Sir, actually, I was asking about that only one-to-one correlation. Sir,
Hmm.
in case of when the flow is like streamlined, we can
Hmm.
the picture you draw means in in this case, sir, we can easily correlate the particles that these particles are
Yes.
moving after an instant of time t1. But in case
Yes.
of plotting the vector, the velocity
Hmm.
vector at the wake
Hmm.
region, sir,
Hmm.
in that case, the flow will be completely, the particles will move in complete random or uh, in a vortex. So, sir, in that small vortices, so, sir, in that case, sir, can we use the one? Can we use this one is to one correlation to find the vortices? Means to get the velocity vectors in the wake region.
Yes, you still can use that. Yeah, that is how it is working. You can still use the correlation. If you have a verticity, say 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you have a verticity, you will just have these particles will just move or just displace like this, right? They will just rotate about their own axis if the particles are
Yes, sir.
there in the. So when you are using the correlation, what we do is whatever the particles present in the previous time step, they will try to map one to one. And the objective function also will try to look at what is the possibility of the maximum displacement of the particle based upon the time scales and length scales. Time scales and length scales means what is your length of the aerofoil, what is your velocity, free stream velocity, and what is the possibility of the movement of any particle, maximum displacement of a particle. So using all these things, you can still correlate that one to one and take the reasonable movement, because any particle cannot reach a maximum of, if it is a verticity also you can it can reach a maximum of u, some u by l scales, I can say, if I'm not wrong, it can reach the u by l scales. U by l scales means it is a velocity by the length. Verticity will come within this time scale. So this scale also you can give as a consideration, and based upon this moment or the time this consideration you can correlate. Like if you want to understand what is the scales, have you seen about the scale analysis? What kind of scales means and how uh, what does it mean? Do you know
Sorry,
about the
sir.
scales? Do you know
No,
about
no,
the
no.
analysis of scalings? Like what I
No,
actually do is, suppose if you have a chord length of L, is it possible that a verticity to generate a more than this chord length L? Some vertex is generating here, which is it possible that it is generated more than the scale length L? Or assume that it
no,
is
sir.
generating some kind of vertices which has a length or some length, any physical parameter that you look at, these are always within the uh, limits of the object or the length, characteristic length that you are stating. So using these kind of scale analysis, you can still correlate what is the possibility of movement of the same particle are moving in this way. These are still complicated things. Well, depends on how better you are defining your function in
Okay, sir.
identifying this correlation. Okay.
Sir,
Yeah.
actually, my doubt was regarding the flapping wing aerodynamics. Professor
Mm.
also mentioned that,
Mm.
sir, in case of a static airfoil,
Okay.
we can find the velocity vector distribution over the entire airfoil. But in
Mm.
case of flapping wings, sir, the thing becomes quite complex. Like to plot the velocity vectors,
Mm.
because so the thing is like it is forming wake, large amount of wake in that case.
Mm. Yes.
So in that video of professor's lecture, means in that lecture, professor didn't
Mm.
go get deep into that topic. But so that's
If you
like
really want to spend some time and interest of understanding this complete PID of things that you have questioned, recent techniques have very good number of papers that you can, like, these are not completely written in any advanced books. Also for advanced levels, you can see some recent good articles of how PID is they are doing. Like you can see professors and papers, also research journal papers. There they clearly mention how they perform the PID and what are the software tools they use and what are the objective functions they use for generating these vector fields. We
okay, sir.
can discuss further on that, like, because it is some advanced concept to discuss all the details of it.
Okay, sir.
Yeah. So if there are no questions, Arhit, if you we can you can meet soon. Let me stop the recording first. So it's